3.2, Introduction to Polynomial Functions. Again, this will have some prior stuff mixed in that we've done with a little bit of new stuff mixed into it. Our objectives: determine the end behavior of a polynomial function. Next objective: identify zeros and multiplicities of zeros. Then we're going to apply the intermediate value theorem, and then we're going to sketch a polynomial function. So once we know all this stuff, we're going to go ahead and sketch at the very end. Okay. So here we go. Start off with a definition. Let n be a whole number, and a sub n minus 1, a sub n minus 2, dot, 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 a1 and a sub 0 be real numbers, where a sub n is not 0. Then the function defined by f of x equals the following. Okay. So that's how we formally write a polynomial function. Okay, so the a terms are the coefficients in front of your x's. Okay, up here in the numerator is what your largest power or largest degree is, and then one less than that, and two less than that, all the way down to your linear term, and then your constant at the very end. Okay, so we know what a polynomial function looks like, but this is how we write it mathematically. Okay, so it is called a polynomial function of degree n. Okay. So it's kind of nice to see how this is written formally as a math definition. But let's put actual examples underneath it. So the first example, we have f of x equals 4x to the fifth minus 3x to the fourth plus 2x squared. Okay. Now that would be a polynomial function. We have our coefficients up front. We have our x values where the degree is one less than the one before that, or sometimes even more than one less. It just depends. If there's no x cubed term, there's no x cubed term. So this would be an example of a polynomial function. When you write these out yourself, you want to start with your largest degree and go in decreasing order. Okay, makes it easier to work with. If you scramble this up, that's going to be hard to graph and hard to work with finding zeros and different things like that. So try to keep it in that descending order. Okay, now this example. Not a polynomial function. Not even close. Okay? So a couple things as to why that's not a polynomial function. Okay, first off, the exponents. Okay, the exponents for this one is a half. That's a negative 1. Okay, well that's not a whole number. Okay, that's not really something we want to work with. Next, that's not a real number. That's an imaginary. Okay, we're not graphing imaginary polynomial functions. That's something you do in like a complex analysis class. So this is not for us. This is not a polynomial function. Although graphing in a complex plane is pretty fun to do. It's not a hard concept once you get the hang of it. Okay? All right. Another quick definition. Functions that form f of x equals a x to the n, where a is a real number and n is a positive integer functions. That does not look like power. Let me rewrite that. That's a little better. Okay. So notice there's no other terms in the sequence for that polynomial. It's just some value raised to the n degree multiplied by some a real number. Okay. So what are some examples of some power functions? Well, let me give you some. Well, I don't think I made that big enough. I'm not gonna be able to fit everything. Let me try that again. Okay. So we got a lot of parabolas there, right? Looks like a bunch of parabolas, right? So what's this gonna equivalent to? So it'd be y equals x squared, this would be y equals x to the fourth, and y equals x to the sixth, okay? All graphed at one coordinate plane. And let me graph some odd ones over here. And this is just, these are rough drawings. So y equals x, y equals x cubed, y equals x to the fifth. Okay, so again, just kind of some drawings of some power functions that have odd degrees and then some that have even degrees. For any power function, y equals ax to the n, the coefficient, A will impose a vertical shrink or stretch of the graph y equals x to the n by a factor of absolute value of a. If a is less than 0, then the graph is reflected across the x-axis. All right. Which we kind of already know that, but we're just applying our vertical shrink and stretch to these power functions here. Okay. Now, do all x to the fourth, x to the sixth, and x squared graphs look like that? No. We know that they could shift a little bit, they could be stretched a little bit. It's just a very generic graph looking at those guys. So in other words, you can pretty much say those are like parent functions, right? Yes?
So if it has even power, it's an even function as far as symmetry goes, and if it has odd power, it's an odd function as far as symmetry goes?
Mm-hmm. Not all the time.
Not, okay, of course.
Because if I add stuff to this, it's going to change where this graph is shifted and stuff, and then that reflection kind of goes away. But for power functions, yeah, that's what you're looking at.
Okay.
Mm-hmm.
That's cool.
I think it's cool too. All right, let's continue. So one thing I want to talk about, and then we'll talk about the leading term test. So consider the function defined by the following. Okay, so I'm just bringing that back over from the definition of a polynomial function. Now, one of the things that we do in mathematics a lot, okay, is that when we see this polynomial function, and I want to know what the behavior of the graph, or just the behavior of the values go to, we focus on this first term in the polynomial, okay? Now, why do we focus on that first term? Well, think about it. If I go to, let me give an example here, just to flush this out. If I had 4x to the fourth plus 3x squared minus 2. Let's say that was my polynomial function, okay? And I want to know what the behavior of the graph is going to look like. Well, the reason why we only focus on the first term is because if I keep plugging x values in, 1, 2, 3, 4, 10, 100, 1,000, this first term is going to get large pretty quick, right? Does that make sense? Is this term going to get large? Yes, but is it going to get as large as this guy in the long run? No. This has the most, lack of a better term, power, okay, in terms of what this is going to do, okay? So that's why we focus on this first term, and we do this a lot in mathematics. So that's what we're going to make a note here. So we're going to say the leading term has the greatest exponent on x. Therefore, as x gets larger, and we're going to ignore the sign. If it was positive or negative, that's okay. We know that it's going to reflect it. That's all it's going to do. But as x gets larger, the leading term will be relatively larger in absolute value than all of the other terms. So pretty much what I just said with that example, okay? X of n, or not x of n, x to the n power will eventually be greater in absolute value than the sum of all other terms. Therefore, the end behavior of a function is dictated only by the leading term. Which is why when you write a polynomial, you want the largest power first. Therefore, it's easier to see the leading term, and then it's easier to graph and find zeros and so forth. All right, so let's talk about the leading term test. And by the way, there is another name for it. You could also hear the words leading coefficient test. Okay? So any one of those means the same thing. Consider a polynomial function given by, I'm going to rewrite the definition of it. Okay. So what is the leading term test? Well, considering that we just made the statement that the leading term tells me how the graph's going to behave, we're going to go ahead and break it up into an even and odd situation, okay? And the good news is I still have the graphs up here so we can see it. So if we have an even degree as a leading term, okay, and let's just say that the a value out front is positive, no reflection. Okay. Then we're going to have something like this. And this is just a generic graph again. But the ends, the end behaviors of an even degree is going to be facing the same direction. Now if it's positive, they're going to be both facing up. Okay? So let me go ahead and write underneath it how we would describe it. So as x goes to infinity, f of x also goes to positive infinity, right? So if I keep going in this direction, my end behavior of the graph is going to keep going positively in that direction. As x goes to negative infinity, okay, so if I'm going in this direction, well, my output is going to continue to go infinitely in the positive direction. Okay. Now you can probably surmise that we're going to do something different when it's a negative. So we just put a little line here. So when a sub n is negative, well, that's going to flip everything, right? So let me go ahead and flip this graph. Don't think I'm going to have space where the n is odd. That's going to be a different whiteboard. I don't think I should squish it on the same board. So let me just flip this. Okay, so it's still an even degree. It's just with the negative out in front, it's going to reflect it across the x-axis. So now how do we describe the end behaviors? Well, like this. As x goes to positive infinity, my function values are going to go to negative infinity. And then as x goes to negative infinity, we can see that my output, my y values, will also go to negative infinity. All right, goodbye graphs. I was hoping to keep them up here a little longer. So far so good. Nothing groundbreaking. We kind of know that already. We're just stating it more in a mathematical sense. So if n is odd, well, we know just by what I erased that the end behaviors are going in the opposite direction. Okay? So let's look at a positive case. What if it was a positive, like x to the fifth? So let me just give you an example graph. Okay? So let's say that was some odd degree polynomial. Don't know what it is, but just some odd degree one. So the end behaviors, as x goes to a positive infinity, f of x will go to a positive infinity. If we go to the negative infinity side with x's, we know that our y values are going to go to negative infinity. Okay? Just get used to writing, your end behaviors using those symbols and notations, because you're going to see these a lot in mathematics as well. Now what happens when it's negative? Well, it just flips things. So let's do something like this. Okay? So just the other direction. As x goes to infinity, we can see that the y values go to negative infinity. And then as x goes to negative infinity, I can see that the y values go to positive infinity. Okay? Now that's going to help us, because the last thing we're going to do in this lesson is graph these guys. So just knowing the general behavior will help, along with finding the intercepts and multiplicities and so forth. All right. Let's use it. Let's show an example. Use the leading term to determine Let's look at part A. And yeah, we'll try blue if it survives. I think this is getting close to being done. Our leading term has to have the largest power. So that's this guy, right? So that's my leading term. I'll call it LC. I'll just abbreviate it. Okay. And we can see that my leading coefficient is going to be a 2. So it's positive. Now my leading degree is 7, which is an odd degree. Let me just do a picture of the end behaviors. So it's odd, so therefore we're looking at these two grids. And because it's positive, I'm looking at this guy right here. Okay? So my end behaviors are going to be like this. One's going to be pointing down, which is on the left-hand side, and the other one's going to be pointing up, which is on the right-hand side. Okay? So given that, I can go ahead and write the behavior underneath it. So if we go to positive infinity, my y values also. If I go to negative infinity, my y values follow that as well. And I get, and this is the cool part, I'm getting all that information just from the first term. I already know kind of what the graph looks like. Let's look at part B. Now, this isn't fully worked out, huh? Now, do we have to fully work it out? No. It would take a long time, huh? You get x minus 1 to the 4th, x plus 1 cubed. I don't think you want to do that. But we could be smart about this. First, let's talk about the leading coefficient. So at the very end, we can agree that we're going to have x to some power, but 2.5 is going to be multiplied by. So 2.5, which is positive, okay. My leading degree, well, this one was easy because, well, it was 7. It was the largest power. I don't have that here because it's not worked out, but I can think ahead of time. What do we have here? We have an x times, when I raise that to the 4th power, there's going to be an x to the 4th there, right? Nothing bigger. And then this is to the 3rd, so there's going to be some x to the 3rd term. I don't even know the exact, is it, you know, what's going on after it. I just need to know what's the largest x term in this binomial. And same thing for this one. So we have x to the 1st, x to the 4th, x to the 3rd, so that's going to be x to the 8th. So that's going to be a degree of 8, which is even. Okay? So again, without actually multiplying the whole thing out, I know it's going to be at least an even degree one. So because it's positive and it's even, we're going to be looking at a graph like this, where the end behaviors are both pointing up. So let me just draw those end behaviors underneath it. Okay? And just to put it here, if it was negative, the leading coefficient term, then it would just be pointing downward. Let's describe it. So as x goes to positive infinity, well, my f of x does. As x goes to negative infinity, my y values will go to a positive infinity. Okay? What do you think? Questions? That was what, first objective? So now let's talk about zeros and multiplicities. Okay? First, I gotta tell you what they are. Definition. Consider a polynomial function defined by y equals f of x. The values of x in the domain of f, for which f of x equals 0, are called zeros. Okay. Another word you've heard in the past could hear the word roots, right? So either if zeros are roots, those would be considered our solutions in a way, right? Because that's when we get the y value to be 0. So graphically, these zeros correspond to the x-intercepts of the graph. Y equals f of x. So let's look at an example. Find the zeros of the function defined by f of x equals 2x to the 4th minus x cubed minus 15x squared. Okay. So right now we're just talking about zeros. And then what we're going to do afterwards is introduce this concept of what is a multiplicity. Because that's going to be important in terms of graphing things. So let's find the zeros. So when is f of x equal to 0? Let's figure it out. So we'll set the whole thing equal to 0 and solve. Now, looking at it, we could see that every term has an x value. So what I can do is factor out the largest one possible out of all of these. So that's going to be an x squared. So I'm left with a 2x squared minus x minus 15 left in parentheses. That's a little easier to work with. Because right now, do we have any techniques to factor or to do something with to a 4th degree? Not necessarily. Now, what's in here, oops, if we can, let's try and factor it. Okay, and this is factorable. The one method I showed you at the beginning of the year was like a guess and check, right? Like come up with 2 factors, see if it works. If it does, great. If not, try again. Let me get you back to that definitive way we talked about in Algebra 2, just so you have the other method. So if you recall, we take the first and last number, which is negative 30, and we try to find numbers that multiply to that and then add to give me a negative 1. Okay? So that would be a negative 6 and a 5. Those two would satisfy it. So here's what I'm going to get. I'm going to put brackets here because we're going to have to expand it. So once you find your 2 values, this negative x you're going to take out and put this in its place. So you're just rewriting the polynomial. So it'd be 2x squared, and it doesn't matter what's first or second. I'll put 6 first. So minus 6x plus 5x minus 15. Okay? I should point out, I mean, this is a longer method, but it is definitive. So because it's been a while since you've seen it, I figured, why not? We'll bring it back just to help you. Next step, factor by grouping. So group the first and last 2 terms and take out a GCF. So the GCF out of the first term would be a 2x, and that will give me a x minus 3. And then the last one, I can take a 5 out. That gives me an x minus 3. Okay? Now, if you do this correctly, you'll see the same binomial pop up twice. And hey, we did. X minus 3 came up twice. So therefore, we get 0 equals x squared. So the first factor would be x minus 3. The second factor is what's left on the outside of that. Okay, so we do 2x plus 5. I guess I don't need the brackets anymore, technically. We don't need those. Okay, so there it is. Now again, could you get there by guess and check like I showed you last time? Yeah. You know, what are factors of 2 and factors of 15 can you put together that when you're done multiplying, you get the original? And with smaller numbers, you can get there pretty quickly. But if they're larger numbers, it might behoove you to try a more systematic approach. Now, let's use zero product property. Let's set each one of these equal to 0 and find our roots. Okay. So the first one, well, take the square root, you still get 0. So that's done. next one, I'll add 3 over, so x equals 3. Not too bad. Okay, last one, I can subtract 5 and then divide by 2. So it'll be negative 5 over 2. Okay, those are our 3 zeros. But, let me ask you this. How many answers should I get? Looking at the original. Yeah, 4, right? That's the fundamental theorem of algebra that tells us that. That was good old Carl Gauss. So, where's my 4 coming from? Well, it's the 0. How many solutions should this guy have? 2, right? So this is actually, like a plus or minus 0. So this has 2 solutions. So there's 2, 3, 4, we got all 4. We're good to go. Now, graphically, that's a big change, okay? So let's talk about that next. Okay? So just looking at it, because these have a power of 1, we call that a multiplicity of 1, okay? Because this has a power of 2, this answer is going to have a multiplicity of 2. That's what we would call it, okay? So let me just put a definition underneath it. Now that we have an example above it that we can reference. So if a polynomial function has a factor x minus c that appears k times, then c is a 0 of multiplicity. It's a fun word to say. K. So let me just put an example after that to kind of cement this. So looking at the prior example, like I was telling you, because this is a solution and we have a power of 2, that's what this is saying. Whatever the power is for this, that appears k times, then this has to have a multiplicity of that k value. So this actually has a multiplicity of 2. I'll put MC2. This only has an exponent of 1, so there's only one answer. It's a multiplicity of 1. This is a multiplicity of 1. Okay? So let's try this example out. Given f of x equals x minus 1 squared, solve for the zeros. Okay? And what we're going to do is graph it at the same time so we can see what's happening and how we can relate to the multiplicity stuff. So let's go ahead and solve. So 0 equals x minus 1 squared. To solve for x, I would take the square root to both sides. But again, the square root of 0 is just 0. So we get x minus 1. Add the 1 over. So we get the solution that x is 1. Okay. Now, because it came from a degree of 2, this actually has a multiplicity of 2. So I'll put that underneath it. And let's continue with blue. I'll put here MC is 2. Now, what does that tell me about the graph? Well, here's the deal. What transformations happen in this polynomial? Where am I shifting it? Left or right? Okay, I'm going to move to the right by 1. So there's what the graph looks like, right? Just a general rough graph of it. Well, is the x or the root or the 0, x-intercept, root or 0, at 1? Yes. Well, with a multiplicity of 2, what that's telling you is that it's not going to cross the x-axis. It's going to touch it, but won't go through it. Okay? If you have a multiplicity of 1, it's going to go right through the x-axis. Okay? So if it's an even number, can you say it bounces? Right? It doesn't go across the x-axis. If it's a odd number multiplicity, it will go through at that point. Okay? So that's what multiplicities do, and that's what's going to help us graphing this. So let me go ahead and write that information down for you. So we call these guys touch points and cross points. Let f be a polynomial function, and let c be a real zero of f. Because again, we don't want nothing imaginary. Then the point C0 is an x-intercept of the graph of f. Furthermore, okay, we have the following. If C is a 0 of odd multiplicity, and where's that blue marker? There it is. That's an important phrase to put there, okay? Then the graph crosses, that's another important word, crosses the x-axis at C. The point C0 is called a cross point. Another important part more in the line. Okay. A lot of times with math definitions, there's so many symbols and terms, it can kind of get a little confusing. That's why I wanted to give you some examples prior that we can refer back to. Okay, that makes it a little bit clearer as to what's happening here. So an odd multiplicity, that would be like the x equals 1, the x equals -5 or 2. Okay, if I were to plot those points on the x-axis, my graph's going to go right through it. Okay, so we call that a cross point. Now, if C is a 0 of even multiplicity, all right, then the graph touches the x-axis at C and turns back around. The point C0 is called a touch point. Okay, so that's the last example. If you take a look at the x minus 1 squared, that had a multiplicity of 2. Therefore, as you can see, the graph did not cross the x-axis, it just touched it at the point 1, 0. So this is going to help us make our graphs a lot more accurate and to know what to expect in the future. Like when we look at a polynomial, like, okay, here's the zeros, where's it going to cross and when's it not going to cross? Okay? All right, so let's give it a shot. Example. Determine the zeros and their multiplicities for the given function. we have 1 over 17 times x plus 1 quantity squared times 3x minus 1 quantity to the 7th power, raised to the 7th power. I do not want to multiply that out, and we're not. We're not going to multiply that out. Let's just solve for the zeros first. So we'll set it equal to 0. Set each one using the zero product property equal to 0. So the 1 over 17 equals 0. Well, we don't have to worry about that. That's not going to give me any solutions. So we get 0 equals x plus 1 squared, and 0 equals 3x minus 1 raised to the 7th power squared, or equals 0. Now, before I even go further, let's talk about something here. So going back to the definition of multiplicity, look at the power. So what's the multiplicity of this answer going to give me? 2, right? That's the power. Multiplicity of this guy is going to be a 7, okay? So before we even know what the answers are, I know what their multiplicities are based on the power. Alrighty? So on this side, we get 0 equals x plus 1. I just took the square root. And then we get negative 1 equals x. So I'll put MC is a 2. Now on the other side, I would, take the 7th root of each side, which you still get a 0, which is equal to 3x minus 1. Bless you. We'll add 1 divided by 3. We get 1/3 equals x. So the multiplicity is going to be 7, because what we started with was a degree of 7. Now what does that tell me about the graph? Well, look up here. If it's an odd multiplicity, it's going to cross. So at 1/3, the graph will cross. This is going to be what? 1/3, 0. So at that point, it's going to go right through it. The first one has a multiplicity of 2. So that's even. So therefore, it's going to touch the graph. Okay? So the graph will touch the point to 0, but it will not cross it. Alrighty. Questions so far? Let's continue. And you could, and by the way, I mean, we're not graphing this one yet, but could you graph it to confirm, like, hey, it did cross at this point, or it just bounced a little bit? Yes, you could. Okay. Let's talk about the intermediate value theorem, which is going to use a little bit of this. And then our last thing is, with all this information, let's graph a function, right? Now that we have all this resources here. We touched on this last year, this theorem. Let's see what it says. Let f be a polynomial function for a less than b, if f of a and f of b have opposite signs, then f has at least 1, 0 in the interval AB. Okay? Now this is pretty intuitive. And what do I mean by that? Let's just draw a graph. Again, sometimes I think some of these theorems and definitions, it's easier to have a picture. And, well, let's do this. Let's say that was my function. And right here, let that be A, and right here would be B. Okay. So this is going to be my interval. And actually, well, that would be, I'll tell you what, let's change that. Change of thoughts. Let's let A be like somewhere over here, and B somewhere here. So I'm going to explain one other thing with it. Okay, so here's my interval. Here's A and B. So if I were to plug in f of A, okay, you can notice that what? The sign's gonna be negative, right? When you plug A in. So if right here was f of A, we know it's gonna be a negative number, right? Because that's where it hits on the y-axis there. Well, if I plug in f of B, okay, and actually, I moved that way too far over. Let's put B over there, okay? So if I plug in f of B, we could see that f of B is going to be positive. So because, bless you, the signs changed from negative to positive, did the graph cross the x-axis? It did, right? That's what this is saying. If your y values change, then it had to have crossed the x-axis for that to happen. So there must be at least one 0. Could you have more? Absolutely. If I move B outside of here, it crosses what? Twice, huh? So again, it's at least one 0 that we're going to find. But if I move this over, we can see that, well, there's actually 2 zeros in that interval. So that's what this is explaining here. We call it the intermediate value theorem. So let's do an example. Show that f of x equals 3x to the 6th plus 4x cubed minus 2x squared minus 4 has a 0 on the interval 0, 1. Okay? So I'm not going to graph it. I'm going to skip the graphing part. I just want to know, on the x-axis, from 0 to 1, does it cross? Okay? And how are we going to figure it out? By plugging it in and comparing the y values. If the y values, the sign doesn't change, then I know it has to. Okay? So let's find f of 0 and f of 1 and make that comparison. So f of 0, that's the easiest. Just plug 0 in. So that gets rid of all your x terms. I'm left with a negative 4 at the end. Okay? Again, that doesn't mean anything yet. We have to find the other value before we make a comparison. F of 1, let's plug 1 in. Okay? So let's see. We have, that's just a 3, that's just a 4, that's 7, minus 2 is 5, minus 4 is a 1. Okay. Now, what do you think? Does the graph cross the x-axis? Does it have a 0 in that interval? Yes. The sign's changed, right? So it had to hit the x-axis for that to work. So we're going to say yes. Exclamation mark, because we're excited. Yes, since f of 0 and f of 1 have opposite signs, then by, we'll say IVF, I'm going to abbreviate. Intermediate value theorem, we know that the function has at least 1 0 on the interval 0, 1. Could have more than one. But we know there's at least one that exists. Okay. So the last little thing, and then we'll graph one to finish it. One little note, and it kind of helps graphing. It's not a huge thing. But if we let f represent a polynomial function of degree n, then the graph of f has at most n minus 1 turning points. Okay. The only problem with this is that it says at most n minus 1. So if you have an x to the 5th function, the maximum amount of turning points would be 4. It could have less than 4, which is possible, but it can't go past 4. And again, I mean, that kind of helps, especially when you're looking at a graph. You're like, did I do it correctly? Well, count the number of turning points at least. Okay, so last thing is let's graph. Let's put all this to use. I gave you the steps for graphing, okay? That was already given to you. That's what this paper is, okay? Just came directly from my notes, so you have it. And that's a good, like, step-by-step. If you ever like trying to figure out what's a good way of doing this, you can follow those, okay? So here we go. We're gonna graph h of x. Okay? Using everything we just talked about. So first, let's talk about the leading coefficient or leading term. So that's a 0.2, right? That's going to be our leading one next to an x to some power. So we know it's going to be positive, which is good. Now, my degree. Well, I know I'm going to have an x times, that's going to be an x squared, and that's just going to be an x. So if I multiply those together, that's what, an x to the 4th? So we're going to have an even degree, okay? Which is kind of nice, because again, you don't have to multiply all that out. Just be smart about it. Just think about what would be the largest power possible. So because of that, we know that the end behavior is going to look like this. They're going to be both pointing up. Okay. Next, let's find a y-intercept. At this point, what you're trying to do is come up with some points that are easy to find, okay? And a y-intercept is easy to find. That's when x is 0. Okay, so let's go ahead and plug 0 in. So 0.2 times 0 minus 1, 0 plus 2 squared, and 0 minus 3. And just to save a little bit of time, when you do simplify that, you get the answer to be 2.4. So my y-intercept is going to be at 0, 2.4. Okay? What do you think? So far, so good? Now, let's talk about the zeros. Let's find the zeros on this guy. I'll put this over here. So zeros and multiplicities. 0 equals 0.2, x minus 1, x plus 2 squared, and then x minus 3. Well, here's the good news. It's factored. I don't have to factor it, so just set each one equal to 0 and solve. So the first one, if I add 1 over, x equals 1. And because the power of what we had originally was a 1, that has a multiplicity, I knew this was going to happen, of 1. This marker's dying. I like this color too. Okay, next one over here. If I take the square root, that's still 0. Subtract 2, so x equals negative 2. And that has a multiplicity of a 2. Because our power was originally a 2. Oh, please hold on. One more. Add 3 to the other side. That would have a multiplicity of 1. Okay. That's sad.
Buckets.
I'll have to get another one. All right. So, what does that tell me? So the graph is going to cross at 1. It's going to touch at negative 2. And then it's going to cross at 3. Okay? Well, let's graph. Now that we have those, okay? So we have, I'll put up here. So here's the end behavior. So it's going to look like this, right? So we can go ahead and put your two end behaviors up there. We have it at 1, negative 2, and 3. I'm going to put points there. So negative 2, 1, and 3. Our y-intercept is 0, 2.4, so that's right here. So I went ahead and just plot our points. So far, so good. Now, it's going to cross at 1. So if my end behavior is like this, it's going to come down. Okay. Oh, I'm sorry. I meant cross at, or no, touch at -2. I'm at the wrong spot. So it's going to touch at -2. So it's going to start here, but it's not going to cross. It's going to like bounce up, right? It's just touching. Well, I got to hit the y-intercept, so it's going to come up here, hit the y-intercept. Now at 1, it's going to cross. So here, it crosses. And then at 3, it has to cross. So it has to come back up at some point. And, oh, I guess I should draw it over there. And then continues infinitely, because that's where my end behavior goes. Okay. Questions? Now, could you, by the way, and this is perfectly acceptable, could you plot additional points to make it a little bit more accurate? Absolutely. This is just a nice little sketch based off of what we just covered. How's that for time?